All right, time for another draftphysics.com, debatephysics.com also, where there are a bunch of 5-minute videos discussing the kinetic energy formula. Okay, that says some rather crazy things about reality. And I claim it's all pseudoscience, fake, phony, never should have been, huge giant mistake, and science doesn't want to hear that. They don't want to correct it, they don't want to fix it, they don't want to explain it, they don't want to prove it. They just want to ridicule and demean anyone who states otherwise, pretty much. So anyway, I found a video by a nice enough fellow, a mathematician, I believe, physicist slash mathematician. I don't know exactly what his degree is in, but clearly authoritative, a teacher once, I believe. Anyway, he does kind of chat videos, which are very kind of nice about physics and about what he's observing when he's reading books and whatnot, and just really nice. So he was sort of reviewing a book called Newton for the Common Reader and just explaining the basic Newton's 3 laws that are described in the book. And so I thought I would chime in and just point out how this isn't Newton's physics. I mean, the physics they claim is Newton isn't Newton, and it's really unfair to Newton. And I think this guy really appreciates that Newton was a very good scientist, spent his whole life devoted to the purpose of finding out these truths about reality. Really did spend his whole life doing it, no other interest really. Did a ton of work and was very careful about what he said. Didn't say too much, didn't say too little. Trying to be very, very clear, and he really hated somebody misinterpreting him or stating he said something he didn't say, or say he stole something, or say any. He really found that really offensive. And frankly, he'd find it really offensive if he was alive today that people are claiming Leibnizian physics is Newton's physics. They're not the same physics, completely different physics, completely different view of how energy works in the universe. Conservation of momentum and conservation of kinetic energy are two entirely different things. They can't possibly be compatible. Anytime you change from a heavy thing to a light thing in terms of moving, migrating the energy, they can't get the same answer. The same quantity won't be conserved. It's just a terrible slander to Newton to claim that his worst enemy in life is his physics. They're basically just replacing Newton's portrait with Leibniz, and it's really, it should be offensive to people who do respect Newton as a scientist. So I figure I might be able to get this guy interested in the subject, and maybe he can straighten me out if I'm just so full of crap, But I don't think that's what's going to happen. But we'll see. See if he's a fair cop. See if he can have a chat about what exactly Newton did say, what Newton exactly believed, because he doesn't believe F equals ma, and he doesn't believe 1/2 mv squared, and he doesn't believe 9.8 meters per second per 1 second squared. He doesn't believe in any of that squared second stuff, and he shouldn't be quoted as saying that's reality. It's just unfair. Okay, so I'll play this little bit because he's talking about how science is about doubting and questioning and looking into it and all that stuff. And oh no, what we found over the last 10 years is science is about avoiding it like the plague. To avoid any controversy, avoid any discussion, avoid it, avoid it, avoid it. And if you can, try to kill the person. I mean, just try to do whatever you can to stop anyone from saying anything counter to the dogma they wish to preach. They have a dogmatic story of reality. It includes entanglement, includes all kinds of nonsense, and we all must believe it. We must recite it, and if we don't, we will be punished. So I'll let him say his piece instead.
Look at even old things and doubt whether you really understand them. So you try to rethink about them, and maybe you just get a new insight about them, which nobody has seen. And this happens pretty often in science. This is how science progresses.
No, it isn't. So there is no progress. You never even fixed plus and minus being wrongly assigned. You can't fix anything that's broken, you just won't re-examine, and you don't produce any evidence. There's, you know it. Okay, this guy's name is, by the way, uh, Joydeep Dutta, Dutta. Um, I think I think if I ask you the fair question, should they repeat the Eddington experiment from space? I mean, they've had 50 years to do it. It takes 5 minutes, and you have 400 times better seeing resolution. Is there some good reason why NASA hasn't done the experiment? I mean, it's the only real visual image experiment, where you're actually bending a visual image, which is really important because scatter can't do that. Scatter can't produce, retain an image's quality, but, gravitational bending can. And we don't have any, they don't bother. That's good science? That's science that's doing its job? No, that's science that's just couldn't care less about the truth and the evidence. It just cares about the story it's telling about wormholes and other fake and phony singularity nonsense. It's a religion, frankly.
Science is never about closing down. Science is never.
So closing down, it's everything about closing it down, shutting it down, dogma. It's about preserving the traditional notions, and they just won't hear it. They won't hear that there's something that says it ain't so. And they invent all kinds of new crap, I don't want to go through LIGO. I can go through all these things and point out, do you really think that's what they're doing?
About becoming stagnant. Science is all up all the time. Is about being dynamic, about being open to change.
It's just not true. I'm sorry. I mean, I wish it was. I wish science was what I thought it was. Always had an appreciation for it. Always liked all this stuff, the history of science, all that stuff, fascinating, interesting, all that stuff. And I should have paid more attention to the fact that they did just crucify Newton for saying something they didn't want to hear, and that we haven't grown up. So it's still the same world. They don't want to hear it. They want the facts to conform to their wishes. They don't want the facts to prove something they don't want to accept exists. And the fact is, the universe is dirt simple. It's all run on momentum. Descartes and Newton and Galileo all had right answers. There's a certain amount of energy in the universe, and it's just banging into stuff, and it's just moving from one object to another object to another object to another object to another object, and that's all it's doing. It's just a mechanical clock ticking away.
Even in mathematics, today a theorem.
All right, so we won't bother with mathematics. So in here in the middle is where he talks about Newton, but I guess I'll just paraphrase some of the comments and I'll just provide some of my chat responses to the laws and the way that Newton wrote them and the way Newton stated it. And again, I could get some direct quotes, but I don't think I'm going to need that, and so I won't. Because I don't think I have to prove to you a statement that I think it's probably true. That's exactly what Newton did say. So we'll start with the premise that Newton believed in 9.8 meters per second squared. He never said anything like that. Okay, it's 9.8 meters per 1 second. So for every second you're in the gravity, you get 9.8 meters. So if you're in for 1 second, you go 9.8 meters per second. If you're in for 2 seconds, you go 19.6. You go 3 seconds, it's 30, whatever, blah, 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 and it just goes on and on. 1, 3, 5, 7, basically the Galilean structure. Demonstrating that the distance you're traveling has nothing to do with how much gravity you're collecting in a moment of time. So if you're traveling across a huge amount of distance in gravity, it doesn't really matter because it's about how much time you're in the gravity. It's a time-dependent force. Now, physics says it's mgh. No, the real truth is it's mgt. It's about gravity, especially. It's about how much time you're free-falling in the gravity. The longer you're free-falling, the more velocity you accrue, and you accrue it exactly at 9.8 meters per second. You fall from 4 times the height, you're only in the gravity twice as long. 4 times the height is twice the time. That's the truth. Okay, and so you've only collected twice the force. You can't have possibly collected 4 times the force. So this gets us to the Leibniz controversy, and that's the one where I'll start drawing some stuff and try to make these arguments as concise as possible. But, it's real physics. So it's clear that Newton just said, momentum. This is the second law stuff. Okay, so the first law is kind of easy. Yes, everything needs something to act on it for it to change. So we're just saying everything has a mass, everything we consider as something, right? So there's two things. There's forces, speed of light stuff. We don't really count that, but obviously it exchanges momentum with matter. So, but we don't really count it. And so we're just going to talk about material things moving. So a material thing is moving, and the simple truth is that it's not going to change its direction, as it doesn't change how much money it has until something interacts with it and forces a change. And the change really just has to do with contact. It has contact with something, and then that something, if it's going this way, or it's going this way, or it's going this way, those two things are going to share their contact. The contact is complete, then they'll share completely, and they'll end up with one thing coming out. But if the contact is in some other way incomplete, then yes, this will partially give away part of its velocity, and the other thing will collect some part of the velocity. But it's always going to conserve the momentum. So the mv is always going to be the same in as it was coming. The same amount in creates the same amount out. I can't change how much stuff is moving in the universe. I can only change what is moving in the universe. So if I do hit something and I hit a bunch of stuff that's got little beads in it, the fact is what I'll do is scatter the little beads. And if I add up the mass and the velocity of all the beads that I scatter, they'll equal what I started with. And if I just diminish this speed, then it'll be whatever I diminished it by. And the mv is always conserved. So that's what Newton, Galileo, and Descartes believe. The mv is conserved. All right. That's essentially what they believed. And the direct statement from Newton is in his second law. In his second law, okay, he clearly states, not in the first sentence, but in the second sentence, he clearly states if you want something to go twice as fast, you hit it with twice the force. You want something to go 3 times as fast, you hit 3 times the force. A completely proportional relationship between the force, okay, and the momentum. Completely proportional. He's basically directly saying they equal the same thing. And if we go more directly to what he wrote, you can see that in his writing, he's conceding there's forces. There's not just objects. There's also forces. And he's talking about gravity specifically. So he writes it a little different. He says the force equals the change in your momentum over the change in time. And what he's saying here is that you can have a rate. So I can make a rate, 9.8 meters per second. I can make a rate of force. And I could also just say, yes, there's a total amount of force. So I could have an interaction where it isn't constantly happening like gravity, you free falling. This is a constant event. It's a long event. It can happen for a very long time. Or I can have an event that's just a total event. What happened through the whole experience. And that would be the force net. The net force is going to be, that net time is going to be a 1. The net amount of time is 1 unit of time. It's a 1. So I can just kill this. I don't need this fraction anymore. And Newton was basically just saying the force equals the change in your momentum. Whatever the change in your momentum is. Okay, I should write a P, of course. Whatever the change in the momentum is, that's what the force is. The force equals the change in the momentum. Again, he explicitly said you want to go twice as fast, you hit it with twice the force. You want to go 3 times as fast, 3 times the force. Explicitly said it. All right, and then they've created this fake F equals ma crap that Newton didn't say. Newton didn't say F equals ma. And if he did say it, he would understand that acceleration is just an alteration of your velocity. It's just a change in your velocity. Okay, it's not something that happens forever. It's not something that happens a squared amount of time. It's not any of that stuff. It's just a simple change in your velocity. That's all it is. It's just a version of velocity. You've exchanged, you've added velocity or you've subtracted velocity. That's all it is. It's just really an addition of a velocity or a subtraction of a unit of velocity. That's all it is. It's not some special thing that happens. It's just a change in the velocity. It's nothing squared here. This isn't per second. So clearly he didn't say it's ma squared. Okay, he didn't say anything like that. There's no squared function here anywhere. And this gets back down to Leibniz. This is Leibniz's physics. So mv was clearly Newton's physics. Momentum is what's the quantity conserved in the universe. That's Newton's physics. This is what's conserved. Leibniz came along a year before Newton published, and he said it's mv squared. Now, obviously, in the Newtonian era, this didn't work. Nobody believed it. Okay, Leibniz was buried to nobody. Nobody accepted it, and they resurrected it in 1730. Madame Chartelet, okay, a completely unprofessional scientist, frankly, did some rickety clay experiments and some silly sand displacement experiments. Completely illogical. Drop round things to dent clay. Dent clay with round things. Dent the clay. Don't penetrate the clay, just dent it with a round object. And they figured that was going to be a linear way to detect something's total energy. When, of course, no, the round surface means the less you dent it, the more you're pushing down on the clay, and the more you dent it, the more you're pushing sideways on the clay because of the round surface. So it was really bad physics. It was bad science. The experiment looked interesting because, it's 4 times the displacement. But it's only 4 times the displacement because there's a catch. Okay, just like rolling an object, I could roll an object at twice the velocity. Okay, 2 velocity, 1 velocity. I could roll it at twice the velocity and it'll go 4 times as far, right? Does that mean it has 4 times the energy? No, because we're back to Galileo again, and it's Galileo. And what does Galileo tell you? It goes half the speed here. It doesn't go half the speed at half the distance. It goes half the speed after it's traveled 3 units of distance. So obviously the friction here is very low because you're moving across the surface very fast, and the friction here will be exactly the same as this. This motion, this total motion at 1v, will be exactly the same as this 1/4 of the motion that happened here. 3/4 of the motion will not be at the same rate of displacement, the same rate that you're giving away your energy. So it looks like, okay, it's 4 times the distance. It must be 4 times the energy. No, it's only twice the energy because you're not giving it away to friction at the same rate, because when you're moving fast, you're not putting as much force into the ground. You're not heating the ground as much. The faster you move across the surface, the less you weigh, the less vibrations you produce into the ground, the less energy you put into the ground, the less you exchange with the ground. The faster your contact, the less complete your contact is, the less electricity. If it's electricity, the less leaks. The faster I go across the surface, the less electricity I'm going to put into the conductor. So clearly I'm losing less energy. So all this is an argument about friction and the fact that the friction is being created by gravity, which means it's Galilean friction, which means you're going to get the same 1, 3, 5, 7 ratio. And here it is, 1, 3. 3 units of distance in the same time you did 1 unit of distance. 3 units of distance, same time as 1 unit of distance. Yeah, that's pretty good. So we'll call that a start. Take a pause and go to the next bit. All right, so let's pick up where we started with Leibniz. So Leibniz proposed this theory with no other argument than this simple proposition that because if I drop 4 pounds, okay, 1 foot, it's the same energy, okay, as dropping 1 pound 4 feet. All right, so 4 units of distance. Because it's 4 units of distance. Now what's not being appreciated, he's saying that this 1 pound will collect force 4 times. It'll collect 4 units of force. Well, it's only in the gravity twice as long, okay? 4 times the distance is just twice the time in the force. So, I mean, how can it make any sense? And we know, again, that this is going to be the first unit of time is going to be this distance. And the second unit of time is going to be this big giant pile of distance. That's how it's going to move. And we know what it's going to land with, which is only 19.6. It's only going to land with 2 units of 9.8. And yet I'm supposed to believe somehow it got 4 units of 9.8. Somehow it got 4 units of energy, even though it was in the gravity twice as long, and only, it says right here, it's only twice the velocity. This can't possibly be equal. This has 1 unit of velocity. The momentums are clearly don't match. All right, this doesn't have the same momentum as this has. And so they're claiming this is the truth, okay? So that's Leibniz's whole theory. It's completely anti-Newtonian. The Newtonians argued against this, obviously, but to no avail in the long run. They lost the argument somehow. But it perfectly describes why this can't possibly make any sense. This is not the same momentum. And it can't possibly mean that this can have more force. It only has 2 units of time. It's only going to weigh twice as much. If I hit it on a scale, it's only going to weigh twice as much. I can only... Okay, so the scale is a really interesting question, right? So here, physics and all of this time it has had to measure gravity, and it's never done this simple experiment of just taking a scale, putting a mass on it, okay, seeing the scale bend, and then taking that scale, that reading, freezing it, and just turn it sideways. Turn the scale sideways and see how fast the ball is released, the mass is released. And my argument would be is that, well, we already know this is the force of gravity. What I've basically done is just collected a certain amount of momentum in the spring. There's a momentum in the spring. The ball is actually falling more than it is. It's spending more time going down than it's spending going up. Okay, that's what gravity is doing. It's 2 actions. One action happens quickly, one action happens slowly, and that's the real difference. So there's a net movement in the sense that you are spending more time going one direction than you are going in the other direction. And so in a sense, you could argue that there's a net amount of velocity down. Okay, obviously you're not moving, but there is a net velocity. And that net velocity will show up here when I do this. When I release, okay, this compression on sideways, I'm going to get a velocity. And if I put an elephant here, you know, if I put the elephant on the scale and then I turn it sideways, it's going to push an elephant. And if I put a mouse on the scale and I turn it, it's going to push a mouse. And it's going to push both of them at exactly the same speed because it's exactly the same force that pushed them into the scale. The force was collected based on their mass. Their mass collected the force. Okay, their mass is the bucket. Their mass is the umbrella. Their mass is the surface of your skin sitting in the sun, getting a suntan. The mass collects the force, and the force is stored in here. And so when I let the spring go, what's going to happen? How fast is the elephant going to move? How fast is the mouse going to move? My claim is 1 mile per hour is the actual answer. Okay, and that that will produce. If I push the scale with 1 mile an hour with an elephant, I take an elephant and I push the elephant 1 mile an hour. I take a mouse, push it into a scale at 1 mile an hour. I will read their atomic mass, their actual weight. Okay, their mass. And so the atomic part is a good thing to bring up because this is all what 1/2 mv squared has ruined physics. So physics says we don't weigh our atomic weight. So if I take the weight of your electrons and protons, it's only 1% of the weight, okay, of your measured weight in gravity. Only 1%. But how did they measure the weight of an electron? They measured the weight of an electron by using this stupid equation, okay, 1/2 mv squared. So what they said was, well, the electron's going this preposterous speed, and we're going to use its speed, okay, to decide how much mass it must have. And so obviously, because they've exaggerated the energy of the speed and the energy it takes to move the electron, they're not appreciating that it's much heavier than they think it is. It's much, much heavier. So by orders of 1,000 magnitude or more, they've undermeasured the weight of electrons and protons because they're measuring it using this stupid v squared term. If they took the square off and measured the momentum of the electron, then they would realize that this, okay, the velocity becomes much more irrelevant. Okay, it's not spectacularly squared, huge, gigantic numbers. So now the mass is going to be much bigger proportion of the equation, the mv. All right, so I can go to all kinds of rudimentary, even grammar school physics, where that's really how to understand everything that takes place. Everything is just a matter of you have a big M and a small v, and you can convert it into a big V and a small m. And these things will equal each other. So I can have a bullet. All right, I might as well do the ballistic pendulum since I hear. I mean, that's just such a telling incongruity. Okay, or the 10-ton train, 5-ton train. Right, we got the 5-ton, we got the 5 mass. We combine it with another 5 mass, making a 10 mass going 1/2 the velocity. So this was going at 10 velocity. Okay, so we start off with a 5 mass at 10 velocity. So we're starting off with a small m and a big v. And what do we end up with? A big m and a small v. Everything looks perfectly rational. We have a 10 mass going 1/2 the velocity. Makes perfectly good sense. The kinetic energy equation says I lost half the energy. It's disappeared. Okay, it went somewhere. And then they'll make up some crap about how, oh, it got hot and it made noises and it did all kinds of things. All pieces flew off. All kinds of stuff happened. Well, you can't conserve 100% of the momentum and then claim you moved a bunch of stuff. I can't hit a bowling pin with a bowling ball, okay, and then have the same momentum in my bowling ball. I can't keep my momentum. I can't conserve the momentum and shoot something into space. I can't make heat and conserve the momentum. You can't conserve the momentum, make other things move. Okay, so it's nonsense. And another illustration of that same principle is in the ballistic pendulum, okay, where you have this simple idea. You take a big heavy thing, okay, with a soft interior. You shoot a bullet into it that has 20,000 joules of energy. Okay, you shoot the bullet into the ballistic pendulum. The bullet has a momentum of, say, some number like 1,000. All right, and what do I have as a result of the experiment? I get 1,000 here in momentum. The momentum's completely conserved. I get a very low velocity. I have a very big mass, big giant mass. Okay, perfectly conserved the momentum, yet I lost, as Professor Lewin would say, 99.9% of the KE is missing. It's gone. It's disappeared. It's nowhere to be seen. Now, what can I say? Can I say it got hot? Can I say something? What am I going to say? Where am I going to say that I lost 99% of this 2,000 joules? Is it really there? And if it is there, if there is 2,000 joules worth of heat coming out of this thing, how did I do all of that? How did I make that heat without using any momentum? I didn't lose any momentum at all. So I can roll a bowling ball into something. I can create a ton of heat with the bowling ball. I can bounce the surface. I can bang it up. I can shoot it up. I can make all kinds of heat, and I don't have to lose any momentum. That's nonsense physics. All right, so that should be enough of a kernel, just to say this is an important subject. Physics hasn't paid any attention to it. They've never proven it takes 25 times the fuel to go 5 times as fast, 100 times the fuel to go 10 times as fast. Nothing even any close to that, okay? No proof of this at all. No evidence, nothing. They just assert it as a dogma, and if you claim it's inaccurate or wrong, you will get ridiculed and pilloried. And it's just a fact. The physics isn't interested in the truth. And I wish you'd talk about that. Yeah, I wish you'd acknowledge that it really isn't interested in any of this elemental physics. It doesn't want to make sure that Eddington was right, that the lightest, smallest thing in the universe is somehow bent twice as much by gravity. So something that's not even barely material is somehow bent twice as much as all the other material things. No, let's not test that and make sure. No. No need. We'll just live with our dogma, our stories. It's just a religion. The stories are written in the book. They won't change the book. They won't edit the book. They won't do a damn thing to the book, except add more unicorns. If you have some wooey thing to say about how there's triple entanglement, how, everything has a third eye and it's chakras and all kinds of stuff, well, they'll probably go for that. So if you want to edit it with more wooey nonsense, they'll probably accept it. But if you try to edit it by saying, no, the universe is dumb, stupid, and simple, it's just a mechanical system with a bunch of shit banging into each other, exchanging their identity. They just exchange what they have. I have $10, you have $5, we crash into each other, we end up splitting the difference. I take 8, you take 7. That's all that's taking place. All right, anyway. Till the next time and such and so forth and whatnot. It's a little ranty. I wanted to get done fast. Blah, blah, blah. But I hope you'll engage in the conversation. I've been doing this for 10 years, arguing that there frankly is a much simpler way to understand the physical universe. I can explain charge. I can explain the double slit. I can explain all of this stuff with simple mechanical principles. And they're all really start on the foundation of Galileo, Descartes, and Newton. they had a hell of a lot of right answers. And everything since then is a lot of wrong answers.